used for differences, and usually small differences. Okay? So again, this is just introducing terms, introducing notation. Next, okay, delta x and delta t are little differences, but there's also this term limit. So I'm imagining that delta t is small, very small, smaller than that. Instead of writing lim as delta t goes to 0, delta t, I introduce another definition. A difference, a little quantity that is smaller than the smallest, in the sense of taking this limit, instead of delta, which is the Greek d, I use the modern Latin d, dt. Okay? Now, if you look at this graph, you see that as I make delta t smaller and smaller, delta x will also become small. Even if my particle is moving fast, like over here, okay, suppose this is my t and this is my delta t. If I make delta t smaller and smaller, no matter how fast the particle is moving, in an extremely short interval, even the fastest particle will move a short distance. Okay? So as delta t goes to 0, delta x must also become smaller. And if you make a smaller delta t, the corresponding delta x will also be smaller. So delta x is also getting smaller than the smallest. Okay? So I use the same notation. I realize that if I take the limit, as delta t goes to 0, delta x also has to go to 0. So I use the same notation for them, this going to 0 business. I don't write lim delta t goes to 0, delta t, delta x, etc. I just remember all of that means dx divided by dt. Okay? So far I've just used definitions. I have not made any calculation yet. Okay? Definition is something very sensible. To make exact measurement of velocity, you go to very, very short time intervals. If you go to short time intervals, the corresponding distance will also become very short. How short? You want both of them to be shorter than the shortest. Okay? And this process will give you a more and more exact value. And you define your exact velocity as the limit of this imagined process. And to write all of these words in short, you say that exact velocity d of t equals dx dt. Dx divided by dt. Now, what is the dimension of dt? Time. What's this unit? Seconds. So it is not a different kind of quantity. It is still time, only it's very, very, very small. Similarly, the dimension of delta x is distance, L, and the dimension of the unit of delta x is, or dx, is just meters. Okay? Of course, you use the meters, and dx will be an extremely small number. If you use kilometers, it will be even smaller. That's not important. The important thing is it is still a distance, a very short distance divided by a very short time. And this line in dx by dt is your usual ordinary division. Okay? It is not a new kind of beast, that's dx by dt. It's just dx divided by dt. It's a ratio. Okay. Now, dt is in the limit going to 0. We are imagining that it really at the end becomes 0. How come I am going to divide by 0 and get a result? How can this make sense? Yes, I'm now suspicious. You know, I'm dividing by 0, the result will be infinity. Will it really be infinity? Why not? But what does change form be? I'm asking for a very simple thing. Okay, let me give you a clue. dt, or delta t, is a small number. Let's say delta t is 0.00001, 10 to the minus 6, 1 part in a million. If delta x was equal to 5, delta x divided by delta t would be 5 million. It would be large. Now, if I keep making delta t smaller and smaller, but delta x was always 5, the result would become infinite. If delta x was also fixed as a constant. But as I make delta t shorter and shorter as delta t is going to 0, what is delta x doing? It's also getting smaller and smaller. Okay? I don't know how small it gets, but it's also going to 0. This means I am really always calculating the ratio of two very small numbers. Okay? And before any of them goes to 0, I first calculate the ratio when they are delta x and delta t, figure out how it behaves, and then take the limit. And it will turn out that that limit is not infinite. The reason is because, if you like to think of it that way, if you divide 0 by 0, it doesn't have to be infinite. Okay? But I'm not really even dividing 0 by 0. I'm just dividing a small number by a small number. I first do the division and work out the formula, and then consider what happens when the number delta t becomes 0. Clear? So it works. You can see that it is not going to go to infinity anyway, because as you see in this graph, okay, as delta t becomes shorter and shorter, delta x is also becoming shorter and shorter, and the green line is just changing position. The slope, the steepness of the green line gives you the velocity. Now, in a very short time, my particle is not going an infinite distance. It's going to go from here to here. A very small distance. And its speed will not be infinite, clearly, in the real world. And this whole thing makes sense. And calculating the exact speed, it will have a real nice number, numerical value. Okay? It's not going to be infinite because my particle is not going to run away to infinity in real life. It will follow a graph like this. Okay? That's another way of saying geometrically with this picture, or in terms of the physics, this is just the velocity of a real particle, saying that if you do the calculation exactly, that doesn't mean it will become infinite. It will not become infinite. And the reason is because in short and shorter and shorter time intervals, it will go shorter and shorter and shorter distance. Okay? We still haven't finished this. We now have a problem. We have phrased, we have written down a problem. We have said, okay, if I want the exact velocity, this is what I want to do. I want to figure out how small delta x is when delta t is very small, and then make a division, and then I'll know the result. Okay? But I have laid out the concept. What does exact velocity mean? Of course, scientists and mathematicians thought about this. It's a very common sense, simple thing. But until Galileo, experimentally, they didn't have even crude measurements of time. See, Galileo was the first person to invent the pendulum. Before that, he was measuring the pendulum's period by counting against his pulses. So experimentally, the measurement was not accurate. And theoretically, this kind of abstract thinking, which now we can relate easily to just common sense, okay, was not developed as mathematics. This was the task of Newton to think about how, how to calculate things with very small numbers going to the limit 0. Okay? Okay. And of course, this thing is the derivative. So we are learning why the derivative is needed, is important. And in the next lecture, we will learn how to calculate it. Okay?